All right, so this is our notes for Thursday, September 25th. We are completing the notes. We started our new unit on electrons and light yesterday. And so today we're just picking up where we left off. So where we left off, I guess we're on the third page of your packet right here. And so we're going to finish up our discussion about electrons and atoms in the terms of what does it mean to be in the ground state of an atom? What does it mean when it's in the excited state? Excuse me. And then we're going to talk about the electromagnetic spectrum. All right. So I just love this topic just because it's cool. So, okay. Picking up with our notes, this is electrons in an atom are normally found in the lowest energy level. The lowest energy level. The lowest energy level is the one that's closest to the nucleus. All right. So let's see. Lowest energy level. Hmm. And it's closest to the nucleus. Closest to the nucleus. All right. This is called the ground state. So the ground state. The ground state is the most stable, lowest energy arrangement of the electrons in an atom. So it's the lowest energy arrangement of the electrons in an atom. So electrons are all at the lowest possible energy level in the ground state. Hmm. But then sometimes atoms can be excited, or these electrons within these atoms can be excited. And when they are, they move to a higher energy level. All right. So an atom is going to gain energy. So it's gaining energy, often in the form of heat or electricity. This is not the only form of energy that can excite an electron, but these are two very common ones. All right, so in the excited state, so now we're talking about an electron has gained energy. So it gains energy in the excited state and it moves to a higher energy level. All right, so let's look at this diagram here. So in example one over here, it shows like the first position of an electron in this inner lowest energy level. And then it has been like intercepted, it looks like, by an incoming photon. All right. And so then that electron is absorbing the energy from the photon, and then it jumps up into this outer energy level. And so you can see it. Basically, the same thing is happening down here, except that the electron is not in the lowest, it's in the second to lowest, okay? But it's got more energy, and so it's jumping out into into a higher energy level there. So when an electron is going to go from the ground state to the excited state, it gain energy, must gain energy. Okay, and the arrows are moving out in this case. Arrows move out. And then in this other example, example two, we'll say, so let's say this is the same, it's the same atom, okay? And so now we've got these electrons in these outer energy levels, these higher energy levels, and it's got to come back down, all right? We know that atoms like to be super stable, and so it's going to come back down. And in this case, with this example here, we're moving down two energy levels. And yesterday we learned that the amount of energy that is emitted or released from this transition is proportional to the amount of energy levels that the electron, let's say, quote unquote, fell from. Okay. It's not really falling exactly, but It kind of looks that way here. So we have the arrow that starts out and moves in. Okay, and when the arrow is moving in, it is going to emit energy or release light. I mean, you could say release energy, emit light. How about that? So release energy. All right. And then, of course, on this one, it's doing the same thing. It's traveling closer to the nucleus, so it is going to release some energy in the form of light. And so, an electron to go from an excited state to a ground state, it must release energy. So, it must release energy. And that is when the arrow is moving from out to in. So, we'll say arrow out to in. All right. And a photon is released. All right, so it says once the electron is excited to a higher slash farther energy level, it quickly loses the energy and falls back to a more stable low energy level, a lower energy level. Not always back to the ground state. Okay, it just depends on the circumstance. It says during this transition, the energy is converted into light. The energy is converted into light. We can see colors emitted from the excited electrons as they drop to a lower energy level if the wavelengths are in the visible spectrum. So, of course, we're talking about our atomic emission spectrum, and we learned about that yesterday. Atomic emission spectrum. And oops, and each atomic emission spectrum is unique for each element. All right, it's like a fingerprint. All right, so we did this a little bit yesterday, but we'll go ahead and do another example. So it says a mixture of elements is heated, and the emission spectrum produced by this mixture is compared to samples of the pure element. Based on the spectra, what is the mixture composed of? So in class, we kind of liken this to if I were accused of a crime, let's say, okay, and I have a fingerprint. They have taken some fingerprints wherever the crime was wherever the crime had occurred. If the police officers only find partial prints, but maybe all of them don't match, it's likely that it wasn't me. Okay, so in this particular case, these are like fingerprints for these different elements. And all of the fingerprints must be present in our mixture in order for it to be, in order for us to assume that, yes, in fact, this element is present in this mixture. So let's look at element D. I'll just get my highlighter here. All right, so this is the first print. Okay, we'll say spectral line. And it's coming in, somewhere a little under 750 nanometers. And we do have one right here. And so then we have this one, and this one is present right here. So far, so good. Here we have this one, it's present right there. We got this one, he's present right there. And just kind of keeps going here. So I would say that this one is present. All right, so this one is definitely in our mixture. Now let's go to a different one. All right, so we'll say this one, is that one there? Well, it is. Is this one there? It is. Is this one there? It is. And so is this one. And so now we have actually covered like all of um, the different wavelengths of light that are kind of coming through. And we don't have any left to match up. So we could stop there, but just for the sake of clarity, we will keep going. So element E, all of them were present. So element G, could that even be an option? Well, is that one there? Nope. Is that one there? Nope. Is that one there? Nope. So it would not even matter if all of them were in the same exact place as our mixture, except for one. Like if all of them matched up, but yet there was another one that the element G had that the mixture didn't have, it couldn't be there. Okay, it has to have all of the fingerprints or all of the spectral lines. Okay, so that's the point. So we would say that element Element D and element E are in our mixture. Okay. All right, so that kind of concludes the part where we're talking about the atomic emission spectra. And now we're going to talk about the electromagnetic spectrum. All right, so we learned yesterday that wavelength and energy are related and they are inversely related. And that means that if you have high energy, okay, that means that you have a lower wavelength. And when I say lower wavelength, I mean that the distance between the peaks, that measurement is, which is usually in nanometers or meters, is lower. It's a smaller distance. Okay. This symbol here, this is the wavelength symbol. Okay. So that's what I drew over here, but not great. So that's wavelength. All right. Wavelength. All right. So that is what that means. It says we say that light has a dual nature because light energy exists as both a particle and a wave. A particle and a wave. The particles of light are called photons. Oops. They're photons, and they're like little packets of energy. So light moves as a wave, and therefore we can measure its wavelength, and its frequency. All right, so wavelength here is the wave. And so let's just, by definition, let's look at this picture. So wavelength. So we're talking about, like I said before, the distance between the two peaks, all right, in nanometers or meters. Nanometers or meters. Okay, something to keep in mind, and really just for the future. And I'm going to make a star here. But in chemistry, we often measure this as nanometers. However, our formulas sometimes require that we convert it to meters. All right. And so if that's the case, our conversion factor is that 1 nanometer. Let's write that as where it's legible. 1 nanometer is going to be equal to 1 times 10 to the negative 9 meters. All right, this is exactly what we were doing earlier in the unit when we were converting between like different numbers. Like I would give you a number in meters and you would have to, move the decimal place and give it to me in nanometers, for example. I mean, that's what we like the example that we just did, but it's no different. Okay, so we have to have that conversion factor. All right, so if the wavelength is the distance between two peaks of a wave, that is the formula. Or I'm sorry, that is the definition. So the distance between two peaks of a wave, and our unit is in nanometers. Meters. Okay. All right, so now let's talk about frequency. All right, so we have in this top picture, we have a wave. It goes over 1, 2, 3, 4 times. All right, so we have four complete waves here. And what frequency is frequency basically is the number of waves per second. All right, the number of waves per second. And you'll see, so this one has four per second. And this one down here, it has 1, 2, 3, 4, 5, 6, 7 per second. All right, 7 per second. So the one down here has a higher frequency, all right, because in the same amount of time, the wave is passing through a point more frequently. Okay, so that's basically kind of like where that comes from. So if we're thinking about both of these, we can kind of relate it back to something that we've learned already. So the question now is, which one of these has the highest energy? We already know that a longer wavelength is associated with lower energy, and that a shorter wavelength is associated with higher energy because they have that inverse relationship. So now we see a lower wavelength is associated with a longer wavelength is associated with a lower frequency. And therefore, that lower frequency must be associated with the lower energy. So think about, let's see, sorry. Okay, so let's look at defining frequency over here. So the frequency is, let's say, the number of times a wave passes through a specific point per second. Okay, and the unit for frequency is hertz. The unit is hertz. This unit is derived from this right here, 1 over the S is per second, okay? And of course, another way of writing that is like this. So we'll look back on that. It's important to know how the units work because if you know what makes up a unit of measure, then you can often kind of work your way through problems without a lot of information. Okay, you can kind of decide these relationships. So we're talking about these relationships, but mathematically we can demonstrate these relationships, and we're going to. All right, so then it says all electromagnetic radiation, which is basically all light, travels at the same speed. All right, so 3.0 times 10 to the eighth meters per second. It's all traveling at that same speed. And so now we're looking down here at this electromagnetic spectrum. All right, so yesterday we talked about wavelengths of light that were within this visible light spectrum. But as you can see, that is only representative of like just a little bit of the entire electromagnetic spectrum. We're talking about really, really long wavelengths or really, really small wavelengths, okay? And really, really high frequency and really, really low frequency. So let's just look at this for a second. Um, you are responsible for knowing the order in which these colors come in the visual spectrum. So sometimes we use Roy G. Biv, okay, blue, indigo, violet. So Roy G. Biv, that is a way that we often will remember. I wouldn't ask you, the specific wavelength of a color, even though we did have it on a table prior. You would want to know like the order in which they come. And you also want to know common like waves that are on this spectrum. So let's talk about it. So we have gamma waves. We have, this would be our X-rays. This is our UV. Then we have infrared, microwaves, and radio waves. Okay. So if you're thinking on, what is the difference between these different things? If we're looking over here to the right, we have gamma rays, so gamma radiation. A lot of times this is coming from outer space. Maybe there was like a huge, maybe like a star went supernova or, some sort of process that released a whole lot of energy in outer space. And so you have these waves that are just traveling. So in space is, they say like space is a vacuum. All right. And basically what that means is there is nothing standing in the way of that wave going forever and ever and ever until something stops it. That's what it's going to do. So as it does, um, let's say we have these gamma rays that are coming at us from outer space, but thankfully we have these like this magnetic field, right? That's like kind of protecting our Earth, and sort of maybe deflecting or at least just protecting us from a direct hit from these gamma rays. But my point is that they're very, very dangerous. And so now we're moving over from like the right side to the left side. And now we see these x-rays. So x-rays, you know that when you have to get an x-ray, they cover up part of your body with maybe like some kind of heavy metal like a lead apron or something like that so that these rays cannot pass through and damage other parts of your body. We just want to concentrate that x-ray right where we need to and nowhere else because x-rays can be dangerous. I shared in class, my mom's a radiologist, and she would always have to wear these little, I guess there's some kind of something that detects radiation over time. And they would check on her and make sure that she wasn't getting overexposed. So they had to turn them into the hospital and um, where they would monitor their exposure to radiation because it's really not safe. All right, now we're moving over to UV. So UV radiation is, just like outside. We have UV. And it can be dangerous. I mean, it's not as dangerous as an X-ray or a gamma ray, but it definitely can penetrate your skin. It can cause small things to happen at the DNA level. And so, yeah, it's a bit dangerous. Okay. And then we've got our visible light spectrum. So the visible light spectrum, we would say probably isn't super dangerous because we are living with a constant stream of visible light all of the time. And now we're moving into waves with even less energy. Okay, so we have our infrared. Infrared is associated with heat often. And then we have our microwaves, of course, like we have a microwave, okay? And then radio waves. So radio waves are also traveling around, but the point is they're all traveling at the same speed. A radio wave is traveling at the speed of light, just like a gamma ray is traveling at the speed of light. The difference is in their frequency and their wavelength. So here we have on this side super high energy. So big E is just energy. And on this side, we have a lower energy. And over here, when we're looking at wavelength, we can see that as we're moving from this direction to this direction, all right, so this direction to this direction, from right to left on our screen, our wavelength is going from really, really small to bigger. Okay, so our wavelengths are getting bigger. All right, wavelength. And so we have our wavelength symbol there. And so here we already know that we have an inverse relationship here. One goes up, one goes down, inverse. And on the other side, all right, so we were really, really small. So we have a really small wavelength over here. All right. And so again, we see this inverse relationship. One is down, one is up, inverse, right? So that is our relationship between wavelength and energy. But now we also have frequency, and frequency is new today. We talked about wavelength yesterday, but frequency is new. So now our arrow is going in this direction, and as we move from left to right on our screen, we are increasing in frequency. So we increase in frequency here, okay, and we're decreasing in frequency here. And so we can see a couple of things going on here. So one thing that we can see is that energy and frequency are going to have a direct relationship. Direct means if one goes up, the other goes up, or if one goes down, the other goes down. Okay, so this is direct. And then over here, one went up, we'll say energy went up, and we went up in our frequency. Okay, again, the same direct relationship. But now we can also make this other connection. All right, so our frequency right here went down, but here we see our wavelength went up. So wavelength and frequency have an inverse relationship too, which makes sense because if energy and frequency have a direct relationship, then it makes sense that frequency would have that inverse relationship with wavelength. Um, that just makes sense. Okay, so let me summarize that over here. Okay, so from a relationship standpoint, we have, we talked about wavelength, We talked about frequency. Hey, sweetie, you look good. I like your stickers. She's getting ready for the homecoming game. Okay, my little daughter. All right, so wavelength. So wavelength, let's say wavelength go is inversely related. I did not leave myself a lot of room to energy. Frequency directly related. Okay, to energy. This is the biggest takeaway here. Okay, and inversely related to energy. All right, and if both of those things are true, then we know that wavelength must also be inversely related to frequency. My handwriting is getting bad because my hand is like moving off of the iPad. Let's see if I can do that better. Inversely. Yeah, so I just needed to slow down there. Okay. So that is our relationship. Those are our relationships. All right, so now we just have a series of questions here and we will close out this video. All right, it says choose the correct term to complete the following statements. So you might want to pause the video because at this point you should be able to answer these questions. And if you can answer them correctly, then you have a really solid understanding of the relationship between these variables. So it says red light. Okay, it's asking, does red light have more or less energy than blue light? Well, we know red light is up here on our visible light spectrum, and it's more toward the less energy side. All right, so it's going to have less energy when compared to blue light. This also means that it's going to have a lower frequency and a longer wavelength compared to the blue light. Number two, a microwave. It's asking, does a microwave have a higher or lower frequency than a radio wave? So I'm looking on here. So here is my radio wave right here. And here is my microwave. And so again, the question is asking, does a microwave have higher frequency or lower frequency than a radio wave? So a microwave is going to have higher frequency because it is to the right of the radio waves on our electromagnetic spectrum. And we know that as we're moving to the right, our frequency and our energy are increasing. All right, so it says it's going to have a higher frequency than a radio wave. And this also means that it's going to have more energy because frequency and energy are directly related, but it's going to have a shorter wavelength because wavelength is inversely related to both frequency and energy. All right, so UV light. UV light has a longer or shorter wavelength than violet light. All right, so violet light is kind of one of the last colors on that spectrum on the higher energy side. And then the next thing is the UV. All right, so ultraviolet light. So ultraviolet light. So if we are on the right side, compared to whatever it is we're comparing to, we know that we're going to have more energy. And if we have more energy, that means that we must have a shorter wavelength. And if we have a shorter wavelength, it's going to have a higher frequency, okay, and more energy. Because if we're shorter for a wavelength, we got to be going in this direction for energy and frequency because they're inverse. All right, then it says ultraviolet light travels at faster, slower, or identical speed as a radio wave. And so the big theme here is that all of this is light and it all travels at the speed of light. So they're going to move at an identical speed, the speed of light, okay, which is 3.0 times 10 to the eighth meters per second. Okay. All right. So that is where we stopped today. So if you are ready, go ahead and move on to our calculations. And also, there is going to be a separate video that goes over the scientific notation piece. All right. Thanks so much.